So, having discussed the types of forces that could be acting on an object and free body diagrams, we're now in a position to apply Newton's second law of motion to analyze the forces acting on an object. Now, let's start with a quick recap of Newton's second law, second law of motion. Newton's second law says that the acceleration of an object equals the net force acting on the object over m. So that's the relationship between the acceleration, net force, and the mass. And we can write this equation in this particular form as well. The net force is mass times the acceleration. So if you're looking at this equation, net force is mass times the acceleration, remember this is a vector equation. And so if you're looking at two-dimensional motion, this actually represents two equations. Okay, so in a compact notation, we've written it as a single equation, but what it really is saying is that the net force in the x direction is mass times the acceleration in the x direction, and the net force in the y direction is mass times the acceleration, y component of the acceleration. So the x component of the net force is mass times the x component of the acceleration, and the y component of the net force is mass times the y component of the acceleration. So those are the two equations. So it's actually two equations that are hiding in this one single equation. Okay, now just a few definitions out here. We need objects in equilibrium. So if the net force acting on an object is 0, okay, what that means, of course, is that the net force is 0, or, like I said, the x component of the net force is 0, and the y component of the net force is also 0. Then we say that the object is in equilibrium. Okay, so we say an object is in equilibrium if the net force acting on it is 0. Okay, now there are special cases. If in addition, now, so if the net force is 0, then so if an object is in equilibrium, it means it's either at rest or moving at a constant velocity. Okay, both situation corresponds to equilibrium configurations because their net force is 0 in both cases. But however, if in addition the object is at rest, then we call that situation static equilibrium. I'm going to write it in short. So that's static equilibrium. So if in addition we know, we are either told that the object is at rest, then we call that a static equilibrium. We call that static equilibrium. On the other hand, if the object is moving at a constant velocity, obviously it cannot be accelerating because the net force is 0, is moving at a constant velocity, then we call that situation a dynamic equilibrium. Okay. So static is if in addition the object is at rest. Dynamic is if it is moving, but of course it could only be moving at a constant velocity. Now, how do we apply Newton's laws and everything that we have talked about so far, free body diagrams and identifying the forces in problems? So here is, well, before we get to that, I need to say one thing, because if you notice, we are talking here about, for example, when we talk about the net force, we are talking about the x component of the net force and the y component. So it's important to be comfortable resolving vectors into components. So here are some questions just to brush up your, just to review vectors and their components before we get into the problems. So these are problems that you've seen before in some of the earlier notes. You've got a vector of length 4 units. What are the x and y components? And again, like I said, we've done this before, so I'm just going to tell you what the answers are. What you have here is the x component is going to be sine theta, and it's going to be negative, and the y component is going to be cosine theta, and it's going to be positive. So the answer here, I'll let you go through this carefully. Just again, like I said, this is more a review. It's -2 and 3.5. On the other hand, here is just working it out algebraically. You're given a vector E and the angle theta. What are the x and y components? X component is going to be this component right here. Whoops. The x component is this component right here. It's going to be positive and it's sine of theta. Y component is going to be negative and cosine of theta. So the answer here is d e sine theta for the x component, negative e cosine theta for the y component. And finally, if you were working with this angle, which is a complement of this one, so if you were given this angle and you had to write the x and y components, the x component would be cosine phi, y component negative sine phi. So the answer here would be, so the signs are going to be the same, but when you're working with sine, the depending on the angle, you're going to have different expressions. Whether it's the cosine of the sine would depend on which angle you're working with. Okay. Again, I just quickly ran through this just to remind you of the kind of stuff that you have to be very comfortable doing when you tackle the problems involving forces. So here is a question involved. This is a static equilibrium problem there where you have an object which is at rest. So what do we have? A construction crew would like to support 1,000-kilogram steel beam. So that's your steel beam with 2 angle ropes as shown in the figure. The rope can support a maximum tension of 5,600 newtons, which means each rope can support a maximum tension of 5,600 newtons. Means that if the tension were to exceed that value, the ropes would give way or would break. Okay, is this rope strong enough to do the job? So notice what you're doing. You're hanging a steel beam by these 2 ropes. Okay, that's the sketch that's given. It's a static equilibrium problem because this beam is not going anywhere. And we need to know what are the tensions in these ropes. Okay, now in all these problems which involve forces, when you're analyzing forces, there's a particular way to approach these problems. The first step is to, I'm going to write that as step 1. Step 1 involves drawing a free body diagram. Now, in this case, the free body diagram, in this case, we're talking the free body diagram of the beam. That's what we want to focus on. What are the forces acting on the beam? Now, when you're drawing a free body diagram in a numerical problem like this, we obviously don't know what the magnitudes of these forces are. So we can't, draw the arrows of the correct length, but it just gives us an idea of the directions of these forces. Okay, what are the forces and what are the directions? So okay, let's draw a free body diagram. The free body diagram for the beam. Well, it's got mass. There's of course the force of gravity or the weight acting in the downward direction. And then we have the 2 ropes. It is hanging from 2 ropes, and they call this rope 1, and this is rope 2. So I'm going to put in an arrow out here. There is the tension in rope 1, which is directed, let me say it's directed this way. And there is the tension in the second rope, which is going to be directed this way. So this is a free body diagram for the situation. Not quite. Let's label the forces. So there's the weight. That's the weight. And since this is the first time we're working through a problem, I'm going to put in all the details. And the object responsible for this, what is the object exerting this force on the steel beam? It's the earth. It's the earth pulling down on the steel beam. And I'm going to call this the tension here. It's the tension force, so I'm going to use the symbol. So that's T1. That's the tension. That's the tension, and this is the tension. This it's the force that that rope 1 is exerting on the steel beam. And here we've got T2, which is again the tension exerted by, since I'm color coding this, I might as well. It is the tension exerted. It's the force exerted by rope 2 on the steel beam. Remember, these are all forces acting on the beam. Okay. Now we're told that these angles here are 30 degrees angles. I'm going to call that angle theta. So looking at the sketch, comparing this sketch with the free body diagram that we have, you can see that this angle is going to be theta, and it's, as it turns out, this angle is also theta. Now there's some simplification possible in this particular problem, and the simplification being, since these angles are the same, the ropes, each of these ropes contributes equally to the tension, or they have the same force. They exert the same force on the steel beam. Why? Because of, in some sense, it's a symmetry argument. These angles are the same. So in this problem, since theta is the same for both ropes, and we look at another problem where that angle is not the same, so we'll get to that. The magnitudes of the tension, of course the tensions are in different directions, but the magnitudes of the tensions T1 and T2 are the same, and let's just call that T. They have the same magnitude. Okay, so that's the first step. We've drawn a free body diagram, identified all the forces. Notice we haven't included, say, a normal force, and that's where the errors would start creeping in. Suppose you throw in another force and said, oh, there is a normal force acting on the steel cable, on the steel beam. And then you say, wait a minute, this is not at rest on any surface, so there cannot be a normal force. So it's very important that you identify the correct number of forces, the correct forces acting on it, get the directions right, and now we are ready to move to the next step. Remember, our aim here is to determine this tension T, because we want to compare this tension to the maximum tension that each of these ropes can support. But the second step here is, step 2. Let's resolve the forces, and this is where what we've done with vectors becomes important. Resolve forces into components. So I've made a little table out here, 3 columns. The first column, I'm going to list all the forces, then the x components, and then the y components. Just like we did with when we were talking about vectors. Now the vectors are all forces, so I'm going to list all the forces in the first column. So what are the forces? There is the weight, the tension T1, that is the tension in rope 1, and then the tension T2 in rope 2. What's the x component? Notice the weight is acting in the vertically downward direction, or along the negative y axis. So it has only an y component, so this is 0. Whoops. That is 0. And here I'm going to write minus, let's read the problem carefully. It's got a mass of 1,000 kilograms, so it's minus m times g. That's the weight. The negative sign, why? Because it's in the negative y. The y component is negative. Okay, it's in the negative. It's in the downward direction. Now we look at the tension T1. That's on the rope to the left. And based on this angle out here, you know the x component is negative t sine theta, negative t sine theta. That's all. That's the best I can do because I don't know what that tension is. And the y component is cosine theta, because looking at this picture, that is the x component, that's the y component, which is t cosine theta. And like I said, the same magnitudes on both, the tensions are the same on both ropes, so that's t cosine theta. Similarly, for rope 2, the x component is going to be plus t sine theta. So this plus t sine theta. And the y component is going to be plus t cosine theta. So I've gone ahead and resolved each of the forces into their respective components, x and y components. Now we move on to the third step, step 3. Step 3, determine the net force and apply Newton's second law of motion. Okay. Well, what do I mean by that? Well, the x component of the net force is the sum of all the x components of each and of all the individual forces. So in this case, well, there's nothing much here because you got negative t sine theta plus t sine theta, okay, which of course is 0. These two terms cancel each other. So in this particular problem, there's nothing here, okay, and by which I mean this equation is automatically satisfied. Whatever the tension is, this equation is always going to be true. Okay. How about the y component? So the net force in the y component of the net force, well, we add them all up, so it's minus mg. Then you have t cosine theta plus t cosine theta, which I could write it as plus 2t cosine theta. Okay. Now we go ahead and apply Newton's. That all I've done here is, well, figured out the x and y components of the net force. Now Newton's second law says, again, this I'm doing it here in this case. You might find this is kind of overdoing it for this particular problem, being a little too pedantic, but later on in some of the more complicated problems, this is the approach that you want to, this is the way you want to approach the problems, and it is very important that you work it out this way, so you can correctly work out the details. Okay, so Newton's second law says that the net force in the x direction is mass times the x component of the acceleration. Net force the y component of the net force is mass times the y component of the acceleration. But we know that the beam is in fact, in this case, we know it's in static. I'm going to put that in parentheses because the beam is in equilibrium, and if we know that if the beam is in equilibrium, it has no acceleration. It's not even moving, so the accelerations are both 0. Well, there is nothing coming out of the x equation. This is automatically 0. There's nothing there. So what we have now is, which focus on the y component of the acceleration being 0. And this, oops, that's not what I meant to do. This equation here, along with this equation and this equation, putting all these together, we get minus mg plus 2t cosine theta is equal to 0. And from here, you can solve for t. I'll let you can, work out the details whichever way you want to do it. So if you are comfortable putting in the numbers right away, that's left up to you. I tend to do it algebraically till the last step. Just a bit lazy. I don't want to punch anything into the calculator till I have to do it. And from here, t equals mg over 2 times cosine theta. Now you're told the mass of the beam, you know the angle theta, and so you can go ahead and figure out the tension. Okay, so once you have the tension to answer the question, then you're going to go ahead and compare the obtained value of T with 5,600 newtons and then answer the question, is it safe? Okay. If T is greater than 5,600, obviously it's not. It's going to be, it'll break. If it's less, then yes, you're fine. Okay. So here is a static equilibrium problem, and again, I want you to focus on the strategy. Don't try and memorize this particular solution, but focus on how we approach this problem. Look at the steps that we followed. You got this first step here, free body diagram. Step 2, resolve the forces into components, and then finally, step 3 is when you apply Newton's second law and work out the details of the problem, what you're supposed to figure out. Let's look at another static equilibrium problem. Bethany, who weighs 560 newtons. Okay, just again, reading the problem, you'll see the weight. Her weight is given. That's not the mass, that's the weight. Okay. Bethany, who weighs 560 newtons, lies in a hammock suspended by ropes tied to 2 trees. One rope makes an angle of 45 degrees with the ground. The other makes an angle of 30 degrees. Find the tension in each of these ropes. So what we've got here is, I'm going to call these, using the same kind of setup that we had for the previous problem. I'm going to call this rope 1. And this here is rope 2. Okay, she's in a hammock, and the angles are specified relative to the horizontal here. So if I were to, put, that's not what I wanted to do. Put a horizontal. We're told that this angle is, let me call that angle theta 1, okay? And this angle here is theta 2. So we're told that one rope makes an angle of 45 degrees, theta, let's call it theta 1 is 45 degrees with the ground. Theta 2 is 30 degrees. So unlike the previous problem, the angles are not the same, and because of that, you will notice that you will soon see that the tension in these 2 cables or ropes are not going to come out to be the same. So find the tension in each of the ropes. Okay. What other information is given? Her weight is given, so just be careful there. W is in fact given to you directly, which is 560 newtons, and that is the weight. That's not the mass, that is the weight that's given. Okay, so just keep that in mind. Let's label. So we've got, I'm going to call T1 the tension in the left rope, and T2 is the tension in the right rope. Step 1, as we did before, free body diagram. Our focus is on the person in the hammock, Bethany. So free body diagram of Bethany. Well, what are the forces? That dot represents the person, the object. Now draw the forces. There's always going to be the weight. Okay, and then we have the tension the two tensions, and I'm gonna draw them so that it is quite clear that the angles are different. So we've got that is the weight, and just to remind you, that's the force that the Earth is exerting on Bethany. That is this is T1. I'm running out of space here, so T1, and I'm just going to call that's the tension, and that's the force that the left rope is exerting, and this is tension T2, the tension that the right rope exerts on Bethany. So we've got T1 and T2. Now the angles, these angles are, that angle is theta 1, that angle is theta 2. So unlike the previous problem here, the angles are specified relative to the horizontal. Okay. Step 2, as I said before, resolve. I'm going to write that here. Resolve forces into components. So we've got the weight, tension T1, tension T2. So listing all the forces acting. Here again, notice we're looking, the object is Bethany and the hammock, all is one object. So there is no floor pushing up on her. The only things holding her are the ropes. And of course, there's a force of gravity pulling, or the weight acting in the downward direction. Well, let's see. The weight is in the negative y direction, so obviously that's 0. And since the weight is being given directly to us, I'm just going to write negative w out there, negative sign because of the direction. The tension T1, the x component is going to be based on the angle that's given. It's going to be T1 cosine theta 1 with a negative sign. And here it's going to be T1 sine theta 1, and that's going to be positive. T2 is going to be, again, plus T2 cosine theta 2 and plus T2 sine theta 2. Again, notice I'm just writing just looking at this sketch and just writing out the components, and that's what I meant earlier when I said you got to be really comfortable resolving vectors into components, because this is just one intermediate step in the larger problem. So once you've got these, once you've resolved all the forces into the components, then we move on to step 3, where in step 3 we're going to write down the net force acting in the x component of the net force is minus T1 cosine theta 1. All I'm doing is adding up these x component of all the forces. So that's cosine theta 1 plus T2 cosine theta 2. Y component of the net force is minus W plus T1 sine theta 1 plus T2 sine theta 2. Okay. Applying Newton's second law, apply Newton's second law. So Newton's second law says that the net force in the x component of the net force is mass times the x component of the acceleration. Y component is mass times the y component of the acceleration. And we use the fact, well, in this case, the fact being the system is in static equilibrium, to conclude that AX equals AY, that these accelerations are 0. And now, since the accelerations are 0, we can combine these two equations that we have. these set of equations with the fact that these accelerations are 0 to get to write down two equations. So you have minus t1 cosine theta 1 plus t2 cosine theta 2 is equal to 0, minus w plus t1 sine theta 1 plus t2 sine theta 2 is equal to 0. These are two equations. Now we got two equations here, and it makes sense because there are two unknowns that we have to solve for, the tensions T1 and T2. So the unknowns are T1 and T2. Okay, so two equations, two unknowns, two equations. So we can use these equations to solve for the unknowns. So we need to determine, now is where we get into the details of this problem. What are we trying to find? Okay, well, we're trying to find the tensions. So again, variations to these problems, you may be given one of the tension, and you may be asked, maybe you're given the tension in one of the ropes, and let's perhaps and the, what am I trying? Okay, so yes, instead of the weight, and the unknowns could be the weight and T2. That's another variation to this problem as well. But here we are supposed to determine T1 and T2. Well, how do we solve this? Well, the easiest way to get to the solution is to pick any one of these equations. Let's say I pick the first equation, and I'm going to go ahead and solve for one of these unknowns. Let's say I'm going to write T1 in terms of T2. Okay, it's easier to just show it here. So from 1, I can write T1 cosine theta 1 equals T2 cosine theta 2. Remember, we know these angles. These angles are known, so you can actually figure out cosine of the angles. And so from here, I can solve for, let me just say solve for T1, which means I can write T1 equals T2 times cosine theta 2 over cosine theta 1. They're both numbers out here. You can figure out the cosine of the two angles, figure out their ratio, and if you do that, you can show that T1 equals 1.22 times T2. And let's mark that equation out. Highlight that equation, call that equation 3. And whenever I write these equations, I would urge you, I do make mistakes, so definitely verify that these are correct. Sometimes I do make errors when I'm doing these calculations. But the procedure, I can guarantee you the procedure, but probably not the numbers that I get. But now go ahead, and what do we do? So we have solved T1 in terms of T2. Now what are we going to do? Wherever we see T1 in the second equation, that is right here, I'm going to plug in equation 3. So I'm going to write that as going ahead and substituting. Let's do it here. Substitute 3 in 2, which means I should have probably, it's a bad color. Sorry about that. There we go. I'm gonna the color coding should probably give you an idea what I'm doing there. So you have minus W plus, wherever I see T1, I'm going to put in 1.22 times T2. That's what I'm going to put in. So I've got plus 1.22 times T2 times sine theta 1 plus T2 times sine theta 2 is equal to 0. Again, like I said, these angles are known angles, so you can figure out these terms out here. So we have, but notice another thing, you have T2 appearing here and here, so I can factor that out. So just a simplification we can do. So we have the minus W plus T2 times 1.22 sine theta 1 plus sine theta 2 is equal to 0. So solving for T2, it's going to be plus W over 1.22 sine theta 1 plus sine theta 2. And if you work this out, these are all known numbers, so you know the weight is given. Sine theta 1, these are all known numbers, so you can figure out tension T2, and T2 comes out to be 410 newtons. Again, please verify my numbers. You can find T2, and from there, once you have T2, you can go back to equation 3. Once you know T2, you can figure out what T1 is. You can figure out T1, and T1 comes out to be about 500 newtons. Okay, and that wraps up this problem.